Welcome to True Projects. In this video, we are going to explain about the project that is enhancing DDoS attack detection and mitigation in SDN using an Ensemble online machine learning model. Before getting into the execution, first let us understand what is the project about. Generally, managing a network as running a big complex system where all the devices they will be constantly communicating to each other to route traffic. So your devices, routers and switches they constantly communicate to each other to route the traffic. In traditional networking, each device has its own rules and decisions to make, which can be a bit like trying to organize a team where everyone is working independently without a central coordinator. This can lead to inefficiencies or difficulties in adapting to new needs. Now enters a software defined networking. So, software defined networking is a game changer in the world of networking. It it separates it separates the control plane, that is where decisions are made about how traffic should flow, from data plane where actual traffic is forwarded based on those decisions. So this centralization of control gives the network administrators a way to manage the entire network from a single programmable interface. So with this SDN, that is software defined networking, they can make real time changes, optimize resource usage, and quickly adapt the network to meet growing or changing demands. It is like having a central command center where everything can be controlled and adjusted on the fly. However, while SDN brings incredible flexibility, speed, and scalability, it also comes up with own set of challenges, especially when it comes to security. One of the biggest concerns is distributed denial of service attacks. Since SDNs has this centralized control, it becomes an attractive target for attackers. If they manage to disrupt the controller, they can affect the entire network. So while SDN makes network more agile and efficient, it also requires a more careful approach to safeguard against these kinds of threats. So DDoS attacks, which flood a network with massive amount of malicious traffic from multiple sources, pose a significant risk to availability and functioning of the SDN networks. These attacks they disrupt the normal operation of the network, making it unavailable or unresponsive. The challenge is amplified by advanced attack types like low rate and zero day DDoS attacks. These attacks are harder to detect because they either generate minimal traffic or exploit unknown vulnerabilities, bypassing traditional detection systems that rely on fixed attack patterns. So, the dynamic nature of network traffic attacks, that is network traffic in SDNs, further complicates the detection process. As network traffic constantly changes, the static detection model becomes inefficient, ineffective against evolving threats. This requires a more flexible approach that can continuously adapt to new attack patterns in real time. To address this, innovative solutions are needed that can combine the inherent flexibility of SDN against will strong security measures, ensuring that networks remains resilient against ongoing and evolving DDoS attacks. So to overcome with all these issues, this project is all about improving the detection and defense against DDoS attacks in SDN networks using machine learning. So here we use an ensemble model which will combine multiple classifiers. So here we are combining multiple models that are Bernoulli naive based, passive aggressive, stochastic gradient descent, that is SGD, and multi-layer perceptron, that we call it as MLP. So these four models are combined in one single ensemble model. So by combining them, the system is able to handle different types of threats, including low rate attacks that can be very tricky to spot. So this approach helps to balance the trade-off between bias and variance, including more accurate results and adaptability to new evolving attack patterns. And to test the effectiveness of the system, here we have evaluated on benchmark datasets that are CICIDS 2019, INSDN dataset, slow read DDoS attack in SDN dataset. So these are the three datasets used which provide varied variety of real world attack scenarios. So by using these diverse datasets, the system can be tested for how well it performs across different kinds of DDoS attacks, giving us confidence that model is robust and can handle various situations that might occur in actual SDN networks. And we have also incorporated a custom generated dataset, so that is taken from the public repository. So this dataset is generated in a controlled SDN environment using Mininet and RYU controller, which helps to simulate a realistic network setup. So here it has been generated through simulated network setup. So this network itself follows a fat tree topology, which consists of 10 switches, and 80 hosts, mimicking a real world SDN network. The dataset contains both the normal and malicious traffic, with normal traffic generated through tools like iperf and ping, and malicious traffic created using SCAPI and HPing3 to simulate various types of DDoS attacks. So the dataset includes 22 different statistical features such as flow descriptors and inter-arrival times, which provides a comprehensive view of the network behavior. These features, these features allows us to perform an in-depth evaluation of a system, ensuring that we can accurately detect and mitigate attacks in real-world settings. So by using this carefully crafted dataset, we can test the model performance in variety of traffic scenarios, helping us to fine-tune the system for better accuracy and efficiency in detecting DDoS attacks. So this is the proposed system. And moving on to the extension to further improve the accuracy of this project in detecting DDoS attacks, we are incorporating voting classifier, which is an ensemble method. Essentially, this approach combines the predictions made by multiple individual models to create a stronger, more reliable overall prediction. By leveraging different classifiers, the voting classifier helps to balance their unique strengths and weaknesses, leading to improved accuracy, robustness in detecting and mitigating DDoS attacks. So the idea is that not no single model is perfect, but when combined, they can complement each other and produce better results. And the other part is that we have built front end using Flask framework to make the system more user friendly and interactive. This interface allows users to test the system, giving them the ability to explore its functionality easily to ensure secure access. We have incorporated user authentication so only authorized users can interact with the system. This setup not only helps to test the system but also ensures that user data and interactions remain secured throughout the process. So this is all about the extension. Now, to coming to the implementation, we have followed the steps mentioned in the flow. So what we have done first is we have imported all the necessary libraries and packages required for the project, such as for data manipulation, model building, and for visualization. For that, we have imported NumPy, Pandas, Seaborn, Scikit-learn, Matplotlib, all of them, etc. Then we have done exploratory data analysis. So in this step, we analyze multiple datasets, including CIC-IDS, DDoS 2019 dataset, IN SDN dataset, slow read DDoS attack in SDN dataset, and own dataset. To understand own dataset is nothing but we have mentioned, right, that customized dataset, that is the own dataset. We have named it as own dataset. And then comes data pre-processing part. So here in this step, we clean the data by removing duplicates and performing data cleaning tasks, ensuring that dataset is ready for analysis. Then comes data visualization part. So here this step involves visualizing the dataset to identify patterns and relationships in the data, helping us to understand the distribution of features and detect any anomalies. Then we convert all the categorical data into numerical values using label encoding technique. So we will be transforming categorical data into numerical values so that machine learning models can process them effectively. Then comes feature selection part. So here we select the features by using select percentile method to identify and keep the most important features, which improves the model performance and reduce the overfitting. Then we split the data into train and test values. So train set is used to train the models and test set is used to evaluate the models. Then we initiate all the machine learning models that we will be building in this project, and we train it with the training set where we adjust and fine tune the parameters to improve the performance. Then comes evaluating the model. So we evaluate all of them using accuracy, precision, recall, and FN score, and we compare the results. Then we compare all the model scores through the graphs. Then comes the part of front end. So a front end interface is developed using Flask, which supports user registration and login and stores user data in an SQLite database for user access. And users, they will be able to provide inputs as feature values on the front end that will be feeded, that will be pre-processed at the back end, that will be feeded to the train model. Pre-processed data is feeded to the train model, and finally outcome will be displayed through the front end of the application, whether there is an attack or not. So this is how we have implemented. Now moving on to the algorithms used. These are the algorithms used in this project. This is the proposed model. This is the extension model. And to implement this project, we need basic requirements, which are hardware and software. Coming to hardware, we need operating system of Windows, processor of 5 and above, RAM of 8 GB and above, and hard disk of 25 GB and above. Coming to software, we need application of Anaconda, primary language of Python, front-end framework of Flask, back-end framework of Jupyter Notebook, database of SQLite 3, and front-end technologies are HTML, CSS, JavaScript, and Bootstrap 4. So this is the overview of the project. Now let us execute. So let's open the code folder which contains source code files. These are the source code files in the code folder of our project. Let us understand each of them, how will they be used in this project. So let us open the CIC DDoS 2019 folder. So these are the different files of CIC IDs to the DDoS 2019 dataset. So we will be loading and we will be merging together in the code. And here in the model folder, we have the algorithm information that will be loaded into the project code during runtime of the application. And here is the custom generated dataset. So this is the dataset, and this is the SDN dataset that we have used in this project. And this is the slow rate SDN dataset. And this is the static folder. This folder consists of files related to CSS, JavaScript, and Bootstrap files, which are important for the visual appeal. Then we have templates folder. This folder contains all the HTML pages used in this project. It typically includes files like index.html, about.html, etc., which represent different pages of the website. And this is the app.py file. This .py file contains the information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in HTML templates. And here we have total 4 notebook files. These are the Jupyter notebook files, which contain the combination of code, graphs, and outputs all in one place. It allows users to write and execute code in individual cells, making it a popular choice for the data science. So in this Jupyter source file, we will be loading the CIC DDoS 2019 dataset. We will be pre-processing it and we will train all the models on that dataset. And here in this custom dataset is loaded, we train all the models and do the prediction for this dataset. Similarly, SDN and slow rate SDN dataset. Here in the sample file, we have the test cases that we will be using in the front end for detecting the attacks. And this is the signup.db file. This file is a database file which is used to store the user information. So this is all about the code folder. Now let us execute. So copy the path of the code folder from the address bar of the file explorer. I'm copying it. Now open Anaconda prompt. It is open. Give the command cd, give the space, paste the copied path. Now click on enter. Here if you observe, current directory is changed to the code folder's path. Now compile app.py file. So give the command python space app.py and now click on enter. This command will execute Python script and perform a runtime check for any syntax errors or logical issues. And after running the app.py file, Flask framework will host the application locally at the default address, which is the local host and the port unless configured differently. So this is the local host and this is the port. Now copy this local link provided by the Flask framework and paste it into any web browser. I'm copying the link. I prefer Google Chrome, so I will paste it in that. Paste the link here, click on enter. This is the web page of the project, which is displayed in the browser. This is developed using Flask framework. So we need to get registered first. Click on register and enter all the registration details if you are registering newly. I have already registered, so I'll directly sign in. Click on sign in and give your username and the password. I've given my credentials. Now click on sign in. We have signed in successfully and we are redirected to prediction page of the project. So here we will be doing prediction for all the 4 datasets that we have trained in this project. So first let's do prediction for CIC IDS 2019 datasets, that is CIC DDoS 2019 dataset. Click on that. So here you can see the parameters, right? These are the parameters need to be entered for this dataset. And based on the given values only, we will be getting the prediction. So the first parameter we have is the forward packet length total. It is the total length of all packets in the forward direction, that is from source to the destination during the flow. It indicates the volume of the data sent by the sender. Then we have forward packet length mean. It is the average length of forward packets in a flow. Reflects the typical size of packets sent in forward direction. Then we have flow bytes. It is the rate of the bytes transmitted per second in the entire flow. It helps to assess the network bandwidth usage. Then we have flow IET max. It is the maximum inter-arrival time between 2 packets in the entire flow, and it indicates the longest delay observed in the flow. Then we have forward IET max. So it is the maximum inter-arrival time for packets in the forward direction, useful for identifying patterns like delayed transmissions. Then we have packet length mean. It is the smallest length of a packet observed in the flows. This highlights the minimum data payload sizes. Then we have packet length max. So it is the largest length of a packet observed in the flow. This reflects maximum data payload sizes, often useful in detecting anomalies. Then we have packet length mean. So it is the average length of all packets in the flow, provides an overview of typical packet size behavior. Then we have average packet size. So it is the average size of all packets, that is including forward and backward directions, combining both the directions for a comprehensive view. Then we have average forward segment size. This is the average segment size for packets in the forward direction. Helps to analyze TCP segmentation behavior. Then we have subflow forward bytes. These are the total bytes sent in the forward direction in subflows, useful for analyzing subdivided parts of the main flow. Then we have initial forward win bytes. These are the number of bytes in the initial TCP window sent in the forward direction. This helps to identify initial communication setup characteristics such as handshake behavior. So this is all about the parameters of CIC DDoS 2019. Now let's enter. So open the sample file. So these are the test cases that we are supposed to give. Let's enter them. So let's enter the first case. So let's enter the first case where forward packet length total is 0. Forward packet length mean is also 0. Flow bytes are 0 and forward IET max is 4313, sorry, 41348. And next we have IET max, that is 0. Packet length min we have 0. We have zeros up to subflow bytes. So let's enter them. And the last value we have is 363. Now click on predict. So this given input, it will be pre-processed at the backend. It will be fed to the train model. Then we will be getting the prediction. So here we got the prediction that there is no attack detected and it is normal. So this case is normal. So when the data it flows in these values, it refers that there is no attack detected in that connection. So then comes this case. So let's try predicting this case where forward packet length is 24. 6 is the forward packet length mean. And then we have flow bytes, that is 2.9. And then we have flow IET max, that is 8112781. And then we have IET max and packet length min is 6. Max is also 6. And packet length mean is also 6. Average packet size is 7.5. And we have average forward segment size, that is 6. Subflow forward bytes we have as 24. And we have initial forward bytes that are 5840. Now let's click on predict and see what will be predicted. Click on that. So here we got the prediction, so that here we can see that there is an attack detected. So when the data has all these values, when the data flows in all these values, we can observe that there is an attack detected. Now let's check with one more case for the same data set. So now let's check with this case where forward packet length total is 0. The first three values are 0. So let's give zeros. And then we have 2 as IIT max, and IIT max, forward IIT max is 0. And the next values are 0 except the last value. The last value is 250. Now click on predict. So here we got the prediction that there is no attack detected and it is normal. So here we can observe that there is no attack detected. You can try with all the cases. Now let's do the prediction for the next dataset, that is slow rate SDN dataset. So click on that. So here you can see the parameters, right? So here we have 4 parameters. We are supposed to enter all these 4 parameters. The first parameter we have is the protocol. It is a protocol used in the network flow, such as TCP, UDP, or ICMP. It identifies the type of communication occurring between the source and the destination. Then we have source port. So that is SRC port. This is the port number of the source device initiating the communication, indicates the application or service on the source device that is generating the traffic. Then we have destination port. So this is the port number of the destination device receiving the communication. It helps to identify the specific device, specific service or application on the target, such as HTTP or HTTPS. The last one we have is BWD header length. That means that backward header length. It is the total length of protocol headers in the backward direction from destination to the source. It reflects the overhead introduced by communication protocols in the reverse direction. So this is all about the parameters. Now let's enter them. We have that in this sheet. So let's try with this case where we have protocol value as 17, SRC port is 37159, and destination port is 53. Backward header length is 24. Now click on predict. So here also given input will be pre-processed and train model will be giving us a prediction. Here we got the prediction. There is an attack detected and that attack is low rate attack. So here you can observe that low rate attack has been detected. Now let's check with this case. Click on prediction, click on slow rate SDN. So here protocol value is 0. All the values are 0. Now click on predict. So here you can observe that there is an high rate attack detected. Here high rate attack has been detected if the values are all zeros. Now let's check with one more case. So let's check with this case where protocol is 6, SRC port is 43134, DST port is 443, backward header length is 180. Now click on predict. So here we got the prediction that there is an low rate attack detected. So we're done with the second data set also. Now let's check with the third data set. Click on SDN dataset. So here we have some parameters which are need to be entered. Let us understand what are these. So the first one we have is DT, that is duration time. It is a total duration time, that is the network flow measured in seconds or milliseconds. It captures the inter-arrival time, that is time interval between the first and last packets in the flow. Then we have packet count. So it is the total number of packets in the network flow, including both forward and backward directions. Indicates the volume of communication in terms of packet quantity. Then we have byte count. It is the total number of bytes transmitted in the network flow, including headers and payloads. Reflects the overall data volume exchanged. Then we have PLT per flow, that is packet length total per flow. So it is the sum of lengths of all packets in a single flow. It measures the cumulative data size exchanged during the flow. Then we have byte per flow. So it is the average number of bytes transmitted per flow. It provides a normalized view of the data volume in relation to the number of flows. The last one we have is the packet rate. So that is the PKT rate. It is the rate at which packets are transmitted in the flow, typically measured in packets per second, that is PPS, indicates the speed of communication and helps to detect abnormal traffic burst. So this is all about the parameters. Now let us enter them. Let's open this sheet. So here we have test cases here. Let's enter them where the first one, DT, that is duration time, is 27888. Packet count is 131264. And the next one we have is the byte count, that is 1.36 E plus 08. That is 135583,872. And then we have packet per flow, that is 29. Byte per flow is 2842 and PKT rate is 0. Now let's click on predict. So this input will also be pre-processed at the backend and then we will be getting the prediction. Here you can observe that there is no attack detected. It is normal. So here you can observe that there is no attack in this case. Now let's check with this case. Click on prediction, click on SDN dataset. So DT value is 32433. PKT count is 27. Byte count is 2646. And PLT per flow is 0. The next three values are 0. Now let's click on predict. So here we got the prediction that there is an attack detected. So your attack has been detected. Let's check with one more case. So let's check with this case where DT is 25121 and PKT count is 7647. Byte count is 504726 and the next three values are 0. Now click on predict. So here we got the prediction that there is no attack detected. It is normal. So here there is no attack detected. So we are done with this SDN dataset. You can try with all the cases if you want. So now let's try with own dataset. So the first parameter here we have is total length of backward packet. So it is the cumulative length of all packets transmitted in the backward direction. It is from destination to the source, and this helps analyzing the data returned by the receiver. Then we have forward packet length max. It is the maximum length of packets sent in the forward direction. Indicates the largest packet size sent by the sender in the flow. Then we have forward packet length mean. It is the average length of means that is packet transmitted in the forward direction. Reflects typical packet size by the sender. Then we have forward packet length of standard deviation. It is the standard deviation of packet lengths in the forward direction. Highlights the variation in packet sizes. Then we have backward packet length mean. It is the average it is the average length of packets transmitted in the backward direction. Then we have forward IIT mean. It is the minimum inter-arrival time for packets in the forward direction. And here we have backward PSH flags. It is the count of push, that is PSH flags set in packet in the backward direction. This flag indicates the receiver should process the data immediately. Then we have packet length mean. So it is the average length of all packets in the flow, that is forward and backward, gives an overview of all packet sizes in communication. Then we have average packet size. It is the average size of all packets combining both forward and backward directions, reflecting typical payload size across the flow. Then we have forward segment size average. So it is the average segment size of packets in the flow direction, indicates typical segment behavior of TCP packets from the sender. Then we have backward segment size average. So it is the average size segment of backward packets, that is packets in the backward direction, reflects typical segmentation behavior of TCP packets from the receiver. The last one we have is the forward initial win bytes. These are the initial number of bytes in the forward TCP flow. This shows the much data the sender can send before requiring an acknowledgement. So this is all about the parameters of custom data set. So let's enter them. We have it in this sheet. So let's open. Let's try with this case. So let's copy the first value, that is the total length of backward packets, and get back to the application and paste it there. And then forward packet length max, that is 78. The next value is 11. And next forward packet length standard deviation is 27.96. Backward packet. So here the backward packet is 3351.73. And then we have IET max, that is 3. And backward PSH push is 2. The next one we have is backward packet length mean, that is 1124. And then we have average packet size. And then we have forward segment size, that is 11. And backward segment size, that is 335, 3351.43. And then last one is forward initial win bytes. So here we have entered all the parameters. Now let's click on predict. So here we got the prediction that there is no attack detected and it is normal. So here in this case, attack has been not detected. Now let's check with this case. So click on prediction, click on own data set. So here the first value is 0 and packet length max is 80. 16 is the packet length mean, and the next one is 16 is the packet length standard deviation. Backward length mean is 0. Forward IIT min is 74. And backward PSH flags are 0. 8.4 is the packet length mean, and average packet size is also the same. And then we have 16 as forward segment size. And then we have 0 as backward segment size. And the next one is 29,200 is initial win bytes. Now click on predict. So here we got the prediction that there is an attack detected. So here you can observe that there is an attack detected from the given keys. So this is how you need to execute. Now let's check with the graphs. Click on graph. So first let's see the graphs of CIC DDoS 2019 dataset. So click on that. So here we got the graphs. This is a sample outcome graph, which shows the distribution of the target class that we are predicting. Here on x-axis, we have the label, that is attacker normal case, and on y-axis, we have the count. Here we can observe that attack are more than the normal cases. And here, this is a correlation matrix. This is the accuracy comparison graph. Here on x-axis, we have accuracy score, and on y-axis, we have all the models that are trained on the data set to predict the attack. And here we have precision score comparison graph. This is the recall score, and this is the FN score. So accuracy, precision, recall, and FN score are the models used to evaluate the classification models. So now let's check with the slow rate SDN dataset graphs. So this is the sample outcome graph. This is the correlation matrix graph. This is the accuracy comparison graph. This is the precision score. This is the recall score, and this is FN score. Now let's see the graphs of SDN dataset. So here we have the sample outcome graph. This is the correlation, accuracy, precision, and recall. Now let's check with the last dataset. So this is sample outcome. This is the correlation matrix. This is the accuracy, precision, recall, and FN score. Now click on logout. In this way, just by giving inputs to the application based on the given input, here attack will be predicted. So this is all about the project.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.